So today's lecture on electrolyte solutions is really kind of a standalone thing. We're kind of in this section of transport properties. That's the next. So these would be a region where we have non-equilibrium systems, things where there's either heat flow, there's mass flow like in gravity, like a centrifuge, or let's see, diffusion, so matter flowing from a high concentration area to a low concentration area. And one of those is conductivity, but I wanted to talk, before we could talk anything about conductivity, we need to talk about electrolyte solutions. The other thing is, this is one of those topics that people that are integrated really wish I had covered earlier, because you need to know about some of these concepts in order to do the nickel glycine lab. And so, so I feel like, dang, I wish I had had this lecture, a month ago. So I'm sorry. It's the same every year. I get to this point and people in integrated go, whoa, what's going on? Yeah, okay, well, that's good. So maybe this will help a little bit with the thermodynamic versus concentration-based equilibrium constants. So let's look at this for a second. Up to this point, let's take this reaction shown here, barium sulfate. And so this would be what I call, like in freshman chemistry, the solubility of insoluble things. Okay, because barium sulfate's insoluble. If you look at the solubility rules, we say insoluble, and then we go and calculate how much is in solution. It ever confuse you? You think, wait a second, that's weird. Well, if it's insoluble, why are we calculating how much dissolved? But very, very little dissolved. I mean, we actually take barium, which at large levels, large doses in the body would be extremely toxic, and we just pump people full of, pounds of it almost. And you think, how is it that they're not killed? Because we pump them full of barium sulfate in order to take an X-ray of their intestines. So it's a barium enema. So they take barium sulfate slurry, and it's unpleasant, but they put it in their bowels. Okay, how they do that you can Google. Okay, and so then they take an X-ray of their abdomen, and because your intestines are soft tissue, they don't really show up on X-ray. But barium's not soft. I mean, it's a hard ball of electrons, and so it provides great contrast for X-rays. So then we can image the lower intestine. Of course, now a lot of that is gone away because we have these advanced endoscopes where we can go in with cameras and stuff. So that's even better than an X-ray. But still, they have barium sulfate slurries. And so the whole point of that being non-toxic is because barium sulfate is so insoluble. So we calculated this in the freshman course using the equilibrium constant, this KSP. And we talked about concentrations, but really it's activities. And if you remember back to statistical thermodynamics, it's really the partition function. And so we're approximating the partition function with these activities. And then if it's going into pure water where there's not a lot of ions already in solution, then we can approximate further and say it's just the concentrations of those ions. So we're 2 approximations down the road, and some of those approximations fail. And when those concentration approximations fail, then we introduce what we call activity coefficients, so that we can get back to something that's what we would call an activity, not a concentration. And the activity is really just an approximation for the partition function that goes all the way down to the quantum levels. Okay? So we can fold in all of that quantum business and strange behavior into this number called an activity coefficient. So for non-electrolyte solutions like ethanol and water, the activity coefficient is 1. So whatever the concentration is you calculate for ethanol, it's going to go into water, it's going to behave, it's not going to be changed by the charge of that solution. But all the ions are going to react to the charge of the solution. And so we need to calculate the ionic strength. We have 2 equilibrium constants now. We have the thermodynamic equilibrium constant, which I would say would be the true equilibrium constant. And then we have the concentration equilibrium constant that we just calculate using the concentrations of those species. So that's the one we've been using up to this point, and that's really an approximation of the thermodynamic equilibrium constant. Because if these activity coefficients here are 1, then K prime equals K. Because you just have 1 here and 1 here times those, okay? And so this concentration equilibrium constant times this, activity coefficients will give you the thermodynamic equilibrium. So let's, what we'll do today is we'll calculate in ionic solutions how we calculate these activity coefficients. And so an activity coefficient just turns the concentration into the activity. Okay? So this is the concentration of species J times the activity coefficient for J gives the activity for J. And then let's say if we had like barium sulfate and it was like let's say if it was this ion was doubled, like it had two of those ions, then it would be A squared, just like it is the concentration squared. So we use those same rules for creating the coefficient, the equilibrium constant.
I think the state of the sulfate is 1, it's not S, it should be AQ, right?
Oh yeah, it should be AQ. Thank you. Yeah, that's a mistake. I must have copied it over and then deleted something. Yeah, so this should be Aqueous. Thank you for picking that up. It's been the same for I don't know how many years, and nobody's ever said anything. So I'm going to give you a sticker here in a second. Okay, so let's look at the effect of this equilibrium constant, this thermodynamic equilibrium, or the concentration equilibrium constant. So if the concentrations in solution change, that changes the concentration equilibrium constant. So let's go back to this. If the concentrations in solution change, then this K prime changes. But the thermodynamic equilibrium constant is a constant. So when we were talking about the equilibrium constant, we're using that word constant, right? But the concentration equilibrium constant is not constant. All right, so but the thermodynamic one is, because it's related to the partition functions, which is approximated by the activities. So this up here, this KSP, which is the activities, that's the thermodynamic equilibrium constant. It's the same. But you get down here, the concentration one changes. Because look here, if the concentration equilibrium constant changes, so do these coefficients. So these go down, this goes up, and that remains constant. So the activity coefficients have a maximum value of 1. And then they'll get lower and lower and lower. And the concentration equilibrium constant goes up. What that means is that the concentrations of the species in solution goes up. So down here we have a concentration of sodium chloride. And we have various equilibrium constants here. We have, this is Kw, so this is the auto-ionization of water. Now, sodium chloride does not participate in water auto-ionizing. So this is water breaking into hydronium ion and hydroxide ions. So where is sodium chloride in that reaction? It's not, okay? But as you get up, and if you're down here at 10 to the minus 6 molar sodium chloride, we have the traditional Kw of 10 to the minus 14. But you get to 0.1 molar sodium chloride, and now Kw has gone up to 1.6. So all your pH calculations will be off, because Kw is not 10 to the minus 14 anymore. It's 1.6 times 10 to the minus 14, because you're in 0.1 molar sodium chloride. How could Kw go up? Well, the concentration of hydronium ion and of hydroxide ion went up. Okay, and so this means that just in salt water, you've got more acid and more base. You've got more ions. So ions stabilize ions. That's the bottom line for today. You could write that down. Ions stabilize ions in aqueous solution. And it kind of makes sense. You're charging up the solution. And so you put a positive ion in that solution, you could have neutral waters around it, or you could have neutral waters that are somewhat polarized by a negative ion some distance away. Eventually, this could go to a really strong brine salt solution where you've just got balls of positive charge and balls of negative charge that are in this sort of ionic solution that are just sliding past each other, and water's there just to sort of lubricate the ions and get them past each other. You can, of course, go too far, and then you have precipitation of those ions. This is KSP for the for the barium sulfate that we were just talking about, and it's going from 10 to the minus 10 here, all the way up. It's going off scale. This is 3.6, okay, and so it's going off scale here times 10 to the minus 10, and as we go to 0.01 here, sodium chloride, 0.1. So first thing we need to do is calculate what's on this x-axis is the ionic strength. And so here's the equation for ionic strength. And all you're doing is you're sort of ignoring what kinds of ions there are and just calculating all the charges that are in solution. So it's the concentration of ions in solution. You don't care if they're negative, you don't care if they're positive. You just want to know how many ions, how many moles of ions do I have in solution. And it does depend upon their charge, okay? And so it's the charge squared, okay? And so then, so for something like barium, that's 2 plus squared, so it's going to have 4 times the effect that sodium has. Sodium is just plus 1 squared. And so you're going to really have a huge effect for things that are triply charged or have a charge of plus 4. It's going to be a huge effect of like a vanadium 4 plus. You know, it's going to have 4 squared, 16 times the effect of a sodium plus on the ionic strength. And so for barium chloride and sodium sulfate, put those together, you're going to have this huge ionic strength. The barium sulfate will precipitate out, and so then you'll have to put in there the very small concentrations of the barium and sulfate, but you'll have high concentrations of the sodium and chloride. And so this is how you calculate that concentration of ions. Now, what's the 1/2 for? They kind of come in pairs, don't they? Yeah, and so you're kind of overcounting. If you got a sodium, you also get a chloride. Okay, and so it's just cutting that value in half because it's saying we got pairs here. So so it's just 1/2 times all of those ions added up in their concentrations. Okay, these activity coefficients are related to the square root of that ionic strength. And so here's some activity coefficients for various species in solution. And so for potassium, it doesn't drop very much. It goes like down to 0.8. Okay, whereas iron ferrocyanide ion, that 4- ion, which is iron surrounded by 6 cyano groups, drops dramatically, almost to 0. Okay, so what that means is it's going to that's going to counteract the concentration. So iron ferrocyanide is going to go into solution more as you add more ions in solution. So you can cause that to be much more soluble. Same with aluminum. Let's talk about aluminum. You can cause that to be much more soluble in salty water than in pure water. So if you put an aluminum substance in pure water, that may not be very soluble. You add more ions, it's going to become very soluble. This has a huge effect in my area of cleaning. You're talking about aqueous baths, and you want to keep those metals, if you don't want to have etching and so on, if you want to get those metals in solution, you put in more ions in your cleaning solution and you'll pull those metals into solution. So let's talk about these activity coefficients, this thing that's been plotted on the y-axis. It's the Debye-Huckel equation. It's a complicated equation. Obviously, it's an empirical fit, but it's got several different new terms in here for you. You have the gamma, which is the activity coefficient for species J. Let's go ahead and use the one on the right. So this was a log-based equation. Let's move over here. So gamma is 10 raised to the power of this mess. Okay, we have Z is the charge on chemical species J. Mu is the ionic strength. And then this alpha J is the effective diameter of the hydrated ion. And that's the thing you have to look up in a table. It's not the diameter of the ion, like if you looked up in the freshman text, the diameter of a calcium ion or diameter of a sodium ion. This is in water. So think about water. You've put this ion in water and you've distorted the structure of water. In fact, you've actually organized it. Entropy has gone down. because now water's not free to move around as much as it wants. It's attracted to an ion. And so you've taken at least 6 water molecules and formed, most often, an octahedral complex around that ion. So you have a sodium ion, and that's a cation. And so you've got 6 oxygens around that sodium ion. And then those hydrogens are pointed out, and they're hydrogen bonding to water molecules around there. So of this octahedral complex, let me just draw it. I'll use copper. So here we have this octahedral copper complex in water. These are not covalent bonds. These are just coordinate chemistry. So they're just associated with the d orbitals on that copper. You'll get a blue substance out of here because of the splitting of the d orbitals. And so this copper ion in water will be blue because of this complex. And so is this the diameter of the ion? Or does it affect the water molecules even further? Do these bond to another water molecule? You know, maybe there's another one here.
But then when does it stop?
Eventually it starts to get more randomized, and you can't tell. So there's some effective diameter in water that may include this next round of water molecules. I would say diameter, or we do diameter in this? Yeah, diameter. So the diameter is alpha J in our terms in these notes. In water, hydrodynamic diameter. So we're talking about ions in water, and this diameter is related to the behavior of that ion in water. Just for the folks that come back to review the video, let me go back to this. So this is the let me see, am I even recording? So this is the alpha J that we're talking about. It's the distortion in water, and it's just empirically determined, based essentially by conductivity measurements. Okay. And so you can change the concentration and see how it behaves, and you say, okay, that must be alpha for this ion. And you change it again for a different ion, and okay, that must be alpha for that ion. And then you tabulate these ions. Yes?
So does the positive charge on the ion have a bigger effect than the overall species?
Yes, and we'll see those in the table. Yeah, so we'll actually be able to look at the alpha values for different ions, and we'll see some strange things. If you just look at the ion like you do it in Gaussian, and you say, okay, this ion's got to be bigger than that ion, you'd be wrong. Okay, it's how the ion impacts water. Okay, and so we'll see some dramatic effects in this table that you would have gotten wrong if I were to ask you which of these ions behave similarly, okay, in water. So let's look at those.
And copper 1 would be different?
Yes, yes. So, oops. Yeah, that's right. Okay, so that's what I mean by effective diameter of the hydrated ion. Okay, another term for that is the hydrodynamic diameter. Hydro meaning water, dynamic meaning it's going to have to be empirically determined. It's when we say effective, we mean it's really not like a hard surface that you can measure. It's how it behaves. Make sense? Yeah. Okay. And then these constants in the Debye-Huckel equation are for 25 degrees aqueous solution. If you get into this where you actually have to use activity coefficients and so on in your work, you probably have some modification to this equation, but I'm just introducing it today. So let's look at these properties. As the ionic strength goes to 0, then the gammas, the coefficients, go to 1. And so then these concentrations behave like the activities. And then that concentration equilibrium constant, K prime, approaches the thermodynamic equilibrium constant. Now for these low ionic strength solutions, less than 0.1 molar, then this gamma depends mostly on the ionic strength. Okay. And then gamma depends greatly upon the charge of the ion. So like you said, copper 1 versus copper 2 are going to be dramatically different in terms of their coefficient, and their activity coefficients. And then for a given ionic strength, gamma is the same for ions with similar charge densities. So if you think about this, this is a 2+ charge, but its effective diameter, that would give you a charge density, right? It's a charge in a space. And so if ions have the same kind of charge density, they'll behave the same. But they may have the same charge, but a different charge density. And then gamma for a given ion will describe its effective behavior in all other equilibria. So if you can use these gammas for precipitation or pH, acid-base reactions, and so on. So let's look at the activity coefficients. And I realize this is kind of a difficult table to see, but I wanted to put it in the notes so that you could print it out and use it. It's from Skoog, West, and Haller, and then they quote this Journal of the American Chemical Society, 1937. So this is old science. Yeah. But there's some interesting things in this table. Let me point a few of them out. Here's water, or hydronium ion, I should say, and that's the hydrodynamic diameter, 0.9 nanometers. It's one of the largest ones on the table. Okay, and it's behaving similarly in terms of its diameter to the 3+ cations. So aluminum 3+, iron 3+, chromium, lanthanum, cerium. So those are some of the largest values. What I find absolutely baffling is this lithium ion, 0.6 hydrodynamic diameter, so that's the effect it has on water, and benzoic acid. Whoa, what's going on with that? See how I said you'd get that wrong? I would get that wrong. I don't know about you.
Is it because it just has a -1 charge?
It's a -1 charge, but it's an enormous molecule. That's crazy. It's 7 carbons and 5 hydrogens and then 2 oxygens. I mean, it's crazy. But what does it do to water? Really, only that charge is on that acid group. And so that's the only part that's really distorting water. The the organic part isn't really distorting water. Water just doesn't care about it. So it's the ion part, the charged part that really interacts with water, and it has the effect on water the same as lithium does. Look at here, there's this phthalate. That's got 2 acid groups on it. It's a benzene group with 2 acid groups, okay? And so those negative charges on phthalate, 0.6, similar to benzoic acid, but also similar to these, we've got nickel 2+, iron 2+, copper 2+, calcium 2+. So that's the same hydrodynamic diameter and as benzoic acid. But they have different activity coefficients. I mean, here are these ionic strings, 0.965 up here, and then for these down here, 0.870, because they depend so much stronger on those ionic strings because of their different charges. Yes.
So for the benzoic acid, is visually, would that diameter be looking down on the acid group? Because if it doesn't affect the water, wouldn't it look distorted like a bulb?
I'm not exactly sure how to draw this diameter on that molecule. Is that related to what you're asking?
Yeah.
So if we drew benzoic acid, this distortion field, I guess, around that acid group would just be maybe just around that negatively charged oxygen, or maybe around both of them if there's delocalization of that charge. And so it would really just be that acid group distorting water's random nature, and it's really an organizational effect is what it is. It's where does the organization go to randomness in water. That's that hydrodynamic radius. Yes?
What
Cerium. And so they've got lanthanides and, let's see, where is that? Here.
It's the proton.
Yeah.
And it's so that's way bigger than aluminum, right? So, but
Yeah, that's right, but the same hydrodynamic.
does it not matter really at all how big they are?
It doesn't appear. I'm going by this chart. It doesn't appear that it does. It's the charge is the biggest effect. And so the charge is going to cause this organizational effect, not so much the size of the electron cloud. Yeah. So I think it's kind of an interesting table, if nothing else. We could use it for calculations, but I think it kind of makes my brain light up. When I try to look at that, I was like, okay, how do these ions behave in water? What's going on with the various hydrodynamic diameters? Here's one that's 1.1, and those are the 4+ ions. So they have a huge impact on water. And they've got quite a bit like size differences. Here's zirconium, and here's tin. Let's see. Tin is here. What's zirconium? It's 40. Yeah, over here. Yeah, so it's, I mean, it's, I don't know. I was thinking bigger, but cerium's on here too, cerium 4+. And so this, the impact of, taking another electron away from the cerium, it actually, you take the electron away and it has a bigger effect in water. Yes.
So do people like alter their ions to get better coefficients for this? Like would they take neon and strip it of 8 electrons to get it better properties or?
I don't know. Yeah. I don't think you could get that. It would be such a high ion. Like in that example, I think it would just rip all the electrons off of water, and go back to neon. Yeah, so it would totally, for some reason, these ions are stable. Okay. You know how it's very difficult to just predict the stable oxidation states for all the different transition metals and things. You put them in water and they stay as stable ions in water. Whereas if you were to ionize something like neon, even 1+, like neon 1+, and try to put that in water, it would steal that electron and get that back. Because the ionization energy for water is lower than the ionization energy for neon. And so it's going to go to the lowest energy state, ionized water versus ionized neon. Okay. So then we take these radii, or diameters, and the ionic strength across this, and we can calculate the activity coefficients. So this is another way to calculate the activity coefficients than the Debye-Huckel equation, because these right here are given in that table. And so you have this alpha J, and you have the, right here, alpha J here, but you also have the gammas in the ionic strength. So if you just calculate the ionic strength and you have this ionic species, you can come over here and you can interpolate in the table. You actually don't even need to use alpha. The alphas are listed here, which helps you use that previous equation. Okay. So let's go ahead and calculate one. What's the activity coefficient for mercury 2+ in a solution that has an ionic strength of 0.085? And so here's the Debye-Huckel equation. The 2+ on the mercury goes here for Z. We go to that table and look up its hydrodynamic diameter, and it's 0.5 nanometers. Okay, so it's right there. And then we have the ionic strength of 0.085. So put all those numbers in, and we get 0.4. Now, if we were to use the table, okay, because let's say we just absolutely hate this kind of thing, then we just interpolate. And so I'll put this on here because you've heard of interpolation, that you may be rusty on it. And so how do you interpolate in a table? So what do we have? We have an ionic strength of 0.085. Let's go use the table. Uh-oh, not up there. So when you have something that's between the columns in a table, you have to interpolate. And even if it's not a linear effect, you can assume between those 2 points it's linear. You'll be off maybe, but it won't be that much. Okay? And so we take, here's this table here. We have 0.05 and 0.1. So the 0.085 is between here. And so this is, if you want to label these 1 and 2, this is Y1 and Y2. This is X1 and X2. And so you're just using a linear line between those 2 points. You make the equation and put in your data point, and you've got it. So essentially, it might be actually easier if we just call this one 0, 1. So we'll take this sort of intercept with the first point. That's the 0.46. And then we have the distance from that point. So that's 0.5 to 0.085. So we want to go that distance between these 2 points. So we want 0.085 minus 0.05. So that's this distance here. And then this is the slope. This is the 0.38 minus the 0.46 divided by the 0.1 minus 0.05. So that is a slope term. This is the x value, and that's b. So we just take this x part, which is the distance from 0.05 to 0.085, and then we calculate and we get 0.4. Yes, same number. Okay. Cool. So you could use the table, you can use the Debye-Huckel equation, but I just wanted to show an example of interpolation because it's such a useful skill. Many times you get in the CRC a table of values, you got the density at this temperature, a density at that temperature, but you're at some temperature in between. Just interpolate. You know, just take those two as two data points, find the line, and then move as far as you need to move along that line, and you've got the temperature.
What if you use the distance from 1.1 instead? Would it still kind of work the same?
It would work the same. You have to start with 0.38 here, okay? And then it would be a negative number, okay? It'd be 0.085 minus 0.1, and so then this is actually negative, so the negatives would cancel, and it would work out. You'd get the same value, but prove it to yourself. It's a good question, and so whenever you have these kinds of questions, say, gee, what if I went down? What if I did this the other way? Do I get the same answer? And you should get the same answer, right? So that's the kind of stuff that's great for your problems notebook. Say, can I do it backwards? And write yourself notes. Don't just start doing the math, but say, what if, here's the interpolation from left to right. What if I interpolated from right to left? Could I get the same answer? And you should be able to. And if you can't, then you've got a problem and you've got to figure it out. Okay. So that's marvelous. That's good stuff. Let's look at some of the impacts of ionic strengths. So find the relative error introduced by neglecting activities and these activity coefficients and calculating the solubility of barium iodate in a 0.033 molar solution of magnesium iodate. So we've got a common ion effect. We're going to have magnesium ions that are not going to participate in the solution. Okay. And we have KSP, which is the thermodynamic equilibrium constant. So that really has a constant. Okay. Okay, so let's move this down. I have to use a mouse now. So are we good with this KSP equation for the barium iodate? We have barium and iodate. There's two iodates, so it's the activity of barium and the activity of iodate squared. Okay. Whoa. Let's get this down. I'm going to have to, let's see. This is before I had the little animation skills. So let me go right here, and I'm just going to do it in this view. Okay, so then we write out the thermodynamic equilibrium constant, where we have the activity coefficients shown and their concentrations. And we want to know the solubility of the barium iodate, and that's essentially going to be the molar concentration of the barium ions after solving this equilibrium question. So we have an equation here, and we want to know the barium concentration. But right now we have 4 unknowns. That's a problem. Right? So we've got 2 activity coefficients that we don't know, and we've got an iodate concentration that we don't know. But in the problem here, we've got this magnesium iodate, which is soluble. So that's going to give us the concentration of iodate. Okay, so there we get the concentration of iodate from the magnesium iodate, and then we've got the activity coefficients from the table or from the Debye-Huckel equation. So we also need to find the ionic strength before we can get those gammas. And so we have the magnesium ions, iodate ions, and barium ions in solution. And so chew on this next equation for a little bit. Oops, let me move that out of the way. All right, so I've got here 0.033. That's the magnesium ion concentration. And we use that in the ionic strength because it's an ion in solution. So all the ions in solution get used in the ionic strength calculation. So this 0.033 moles per liter of magnesium, and it's 0.066 because we get 2 of those moles per liter of the iodate. Okay, and then what is this? It's roughly 0 for the barium.
Because take all the barium.
Yeah, the barium is essentially insoluble, barium iodate. All right, so it goes away. Now we can calculate the solubility of insoluble things. That's what these problems are about, right? It's going to be a really small number. Okay, so we will calculate what that is, but for now, for the ionic strength, it does not compete with these. These numbers are in the hundredths place, and the barium is going to be way down below. So it's really not going to impact the ionic strength. The ionic strength is probably only going to have 2 significant figures, and so this will be down in the 6th or 7th decimal place. So it's not going to matter at all, leaving that barium concentration out. So if you're looking at this and you're like, wow, I can't solve this problem because in order to solve for the barium, I need to know it. Okay, you make an initial assumption that it's 0 because it's really close to 0. And then you get to the end and you see how big it is and you go, oh, was that a good assumption or not? If you get to the end and it was 0.1, that was a bad assumption to call it 0. Okay, but it's not going to be the way this works out because it's such a small KSP, 10 to the minus 9. Okay. So all the concentration of barium times the concentration of iodate plus some modifications are going to give us a number that's 10 to the minus 9. So it's going to be a small number. Oops. And so then we'll go down a little further. So from table 8.1, a couple of slides earlier, we can look up the barium gamma and the iodate gamma using this ionic strength of 0.1. Okay. And so now we know all the parts of our equation except the barium concentration. And so this is the solubility with activity coefficients. So with these numbers in there, I've solved for the barium. It's 1.56 times 10 to the minus 6. So on this scale, that is essentially 0, right? We compared to 0.03 and about 0.06, something times 10 to the minus 6 is not relevant. Okay.
That's how many moles per liter?
Yeah, and that's, so,
That's crazy.
yeah, 10 to the minus 6 moles per liter in solution. But that's important to know if you're going to drink this. Okay, now I'm not worried about the iodate, but I'm saying that, we can calculate, say, how much lead is in the drinking water just in natural equilibrium with the insoluble lead species. And, it's not going to be 0. But is it going to be below a physiological effect? I mean, is it going to be, low enough that you can drink it? That's sort of I've used that example, not that we necessarily use these things for drinking water, but it sort of gets the point across, right? If it's you can calculate how low it could be. Okay, now that's with the activity coefficients. What about without? What would be, if we were to ignore the activity coefficients, they would essentially be 1, right? You'd have 1 there and 1 there, the activity coefficients. And so if we were to ignore them, get rid of them, make them 1, then we would get a different concentration of barium. And so without the activity coefficients, it's 0.36 times 10 to the minus 6. Now, the reason I wrote it as 0.36, so you could compare it to the other. And so we're quite a bit off. If we were to just use our freshman chemistry way of doing this problem without ionic strength and without all of that, we would get 0.36 times 10 to the minus 6. But in reality, it's 1.5. So it's about 3 to 15. So 5 times higher. So that's a big amount of error. Okay. So, yeah, so that's 77% off. So it would essentially be 5 times higher than what it was. So they're important. You'd get the wrong answer if you didn't take into account the ionic strength. And y'all are finding that out in the nickel glycinate lab. I don't know anything about that lab, but I've heard that when you need to use activities, because when you're in ionic solutions or highly concentrated solutions, then you need to take into account the activities. Let's look at one that's a titration example. So what's the pH of 0.12 molar nitrous acid that also has 0.05 molar sodium chloride in it? Okay, so we've got salty water, tap water. Okay, I don't know if it's 0.05, but it's pretty salty. So it's going back through the ice table problems. We got nitrous acid and water gives hydronium ion and nitrite ion. Okay, and here's our acid constant. This is the thermodynamic equilibrium constant using activities, and here's the Ka for that nitrous acid. And so we have the gammas in front and the concentrations in back, and we got an equation with a whole bunch of unknowns in it, but we can look up all those gammas. Now, for every hydronium ion, we get a nitrous ion. So we're going to, a nitrite ion. So those are equal to each other. So it's essentially the H3O plus squared. Everybody follow that step from freshman chem? Since the NO2 minus is equivalent to the H3O plus, that's going to be the same number. So it's that number squared in the numerator. And then it's a weak acid, so not much of this actually dissociates. And so we can say it was 0.12 molar to begin with. It's roughly 0.12 molar to end with. So we have this for the parent acid as 0.12. And then now we're off to the races. We can use our activity coefficient table and fill out the rest of it. So first we calculate the, that's just solving that for the pH, the minus log of the hydronium ion concentration. And now we can do our ionic strength. So our ionic strength, 0.05 molar sodium chloride, they're both singly charged. And so then it's 1 squared and 1 squared. We have 0.05 moles of cations per liter and 0.05 moles of anions per liter, and the divide by 2. So that tells you sort of the concentration of the salt in water, 0.05. That's the ionic strength. Using the table, we get these activity coefficients. And notice this one. This is the one where you might screw up. This is the nitrous acid. It's not charged. And so these activity coefficients are really taking into account the distortion or organization, if you'd like to think of it that way, of water due to the charge. And so uncharged species have a gamma of 1. Okay. So that should emphasize it. So this nitrous acid in solution, the weak acid, is not really organizing water very much. And so it doesn't have a hydrodynamic radius. It doesn't have there's no effect related to the activity coefficient. And so it just isn't, it doesn't give you an activity coefficient. It's just 1. But the others do. So hydronium ion and the nitrite ion, we look those up. It's 0.086 and 0.86 and 8. And so we put all those into the equation. We get 2.03 for our pH for this. Now that's with activities. So what is it without the activities? 2.1. It's different. It's not a lot different, but it's different. That's the point. Okay. And let me just show you one more that's kind of funny. We get to buffering. So the supplemental material talks about sort of the Henderson-Hasselbalch equation and the buffering region. So here's pKa. And so if we just did an example with activity coefficients and talking about changes in pH, here's the stoichiometric point, and halfway to that endpoint would be the buffering region. Notice right here we're adding a whole bunch of base or acid, depending, and the pH isn't changing very much. It's a very shallow slope there, and that's what we're talking about with buffering. It can handle swings in acid and base without changing the pH much. And so when we get to this, we've got this chart of this volume of titrant versus pH, and you see all the different buffering regions based upon the different pKa's. And so here we can estimate the pH of an aqueous buffer solution, and we've got the the equilibrium here, and we come down, we've got the Henderson-Hasselbalch equation, we can calculate the pH. But what's the deal here? If we were to calculate the ionic strength of that solution, okay, if we look at the concentrations, 0.2 and 0.1, our ionic strength would be 0.9 molar. So in our buffer solutions, where we're putting in lots of conjugate base, like sodium acetate, sodium hydrogen phosphate, all of these salty compounds, our ionic strength is through the roof. Okay, and in fact, if you go and try to use any of the tables with this ionic strength, you're not going to find values that's off scale, if you will. And so what do? Well, we use a pH probe and we titrate to the exact pH we want. Okay, so if you're trying to really calculate an accurate pH by making up a buffer solution with an acid and its conjugate base, or let's say you take acetic acid and you want to make an acetate buffer, you can just start with acetic acid and start to titrate that. And now its pKa is like, I think it's 4.5, and so that'll be the ideal buffering region. And so you would, if you pick the acetate buffer system because you wanted to buffer something to pH 4, then you could start with acetic acid and adjust it with sodium hydroxide to where it's right at pH 4, and it'll have a good buffering capacity. Don't have to worry about trying to calculate it using an ionic strength because it's going to be off scale. So just leave you with that. And I think that's it. I've got the tests and we can pass them out in the hallway.